Hello wonderful person, this is Anton, and today we're going to go back to James Webb Telescope that was recently launched from South America, and we're going to discuss some of the other potential facts you might have not known about the telescope, about the launch itself, and some other stuff I did not get to mention in that first video that you can as always find in the description below or in that pop-up thingy that should be somewhere above my head at some point. And actually, one of the main reasons I wanted to make this is for that one question that kept popping up all over social media, including from a lot of my friends, about this one thing everyone observed but nobody knew an answer to. You might be actually able to see it right here in this image from NASA of the launch itself. Look at the graph below where it says altitude and look at the shape of the graph. Sometime right after the launch, the telescope actually started losing altitude, and it did so for quite a while. As a matter of fact, several people I know panicked thinking that it was a failure and the telescope might actually start falling down because it was not gaining enough altitude. But here we're talking about some of the most advanced launch in history with some of the most experienced engineers and of course rocket scientists from ESA, from the European Space Agency, and they knew exactly what they were doing, and they did this maneuver for a very specific purpose. So let me explain to you why this was so and what's actually happening with this unusual curve you see right there, and why the telescope at some point lost approximately 50 or so kilometers of altitude, but in the end this was necessary to make it even more efficient in terms of launch. And by the way, after the launch was finished, NASA was absolutely shocked at how incredibly efficient this launch was, allowing them to actually save a lot of fuel for future maneuvers. More about this in a few minutes. So, this right here is technically known as the Oberth effect, named after a famous Austro-Hungarian/German physicist who was working on this effect back in the 30s. And this unusual effect that applies to orbital maneuvers is somewhat counterintuitive, but it actually is a great way to acquire extra velocity and thus extra energy by using the least amount of fuel. So in essence, the way it works is, let's say that currently your object has an orbit that's more circular and a lot closer to planet Earth, but you want to take the spacecraft far away from Earth and give it a much more eccentric orbit at first, and at some point make it actually leave the gravitational well of planet Earth entirely. And obviously to do this, you would want to start increasing the speed of the spacecraft until the orbit stretches so much that it essentially leaves the planet itself. But the question is, where exactly do you start firing your engines? Well, it turns out that mathematically, if you were to fire your engines right here at the farthest point, known as apoapsis, or the farthest point away from the orbit, this would give you the least amount of efficiency. So you really don't want to fire your engines there unless your purpose is to return to Earth and to decrease the orbital parameters. On the other hand, by firing your engines right here, almost right here, at the periapsis point, the closest approach to planet Earth. Okay, here we go, much better. At this point, by spending the same amount of fuel, you actually get a tremendous boost of energy that allows the spacecraft to then increase the total orbit with much more efficiency than it would be possible otherwise. In other words, you gain the most kinetic energy by applying as much speed as possible at the closest point of orbit. And it turns out that in many different cases, it actually might be even worth it to spend a little bit of fuel to slow the spacecraft down or to have it fall closer to the planet, or essentially enter the gravity well of the planet even further down, in order to get the highest boost of energy afterwards by getting as much velocity at that lowest point. Which is precisely what's happening right here. By allowing the rocket to slowly fall a little bit closer to planet Earth, but still above the atmosphere where it's going to slow down the rocket, it allowed the European Space Agency's engineers and rocket scientists to get the highest possible boost out of the least amount of fuel. And this is actually a really important maneuver because if you remember from your physics class, the kinetic energy formula for kinetic energy is E equals mv squared. The velocity here is squared. So for every single piece of velocity gained, you actually get a square of energy. In other words, by boosting the spacecraft at that lowest point, you get a square amount of energy, which is extremely efficient for a spacecraft that's trying to save as much fuel as possible. And this is also something that can be efficiently used by different slingshot maneuvers as well, also known as the gravity assist maneuver, that's been used by pretty much every major interplanetary probe. This is the example from the Voyager 1 probe. And so here, as the probe approaches the planet, by firing the boosters at the closest approach to the planet, you actually get a lot more out of it than you would otherwise. For example, by firing your rockets on approach to Jupiter, if you had a periapsis velocity of 50 km per second and you performed a 5 km per second burn, your final velocity would actually increase by approximately 23 km per second as you move away from Jupiter, giving approximately 4.5 amounts of boost than you would have otherwise if you did not approach the planet. And that's actually why, in certain situations, if you're trying to reach really faraway objects, like for example Pluto, it might be actually more efficient to first come closer to the Sun, or specifically a planet like Venus, and get a boost from Venus first, and then as a result get a lot more energy otherwise. But that's of course in regards to interplanetary probes. When it comes to James Webb Telescope, this maneuver right here was in essence initiated for really two purposes. One of the reasons was because the second stage of the rocket here is just not as powerful as the first stage, so the telescope would still very likely lose some of the altitude as the engine picks up speed. But at the same time, this was necessary because the telescope is generally trying to leave the orbit of planet Earth and get an extremely extended, extremely eccentric orbit. So in other words, none of this was an accident and all of this was technically pre-planned. Then following this, there was another really interesting maneuver that you see right here. The telescope was sort of wiggling around and moving around just a little bit. It did look like it's losing control, but in reality what it's actually doing here is moving the telescope so it doesn't always face the Sun, to prevent any potential damage from the Sun, because the actual instruments on the telescope were extremely sensitive. Something that had to be done because the final orbit of this telescope is a little bit more complicated. But it turns out that the initial ESA's launch was so efficient and so extremely accurate that that first boosting maneuver turned out to be extremely minuscule, saving a lot of fuel in the process. Because of this, the NASA scientists are now thinking that the final mission of the telescope is going to extend way past the initial date. Initially, because of the limitations when it comes to fuel, the original plan was to maybe have this telescope for about 5 to 10 years, and after this it would probably retire. But because of this fuel-saving maneuver, it turns out that now the mission might be extended even further, meaning that this telescope might survive for 12, 15, or even longer years. And that's the main reason why the telescope has a limited functionality, because of the fuel. As you can see from the simulation, it's going to have what's known as a Lagrange 2 halo orbit, and this requires just a little bit of fuel every year to maintain the orbital parameters. Here it only needs to change its velocity by approximately 2 meters per second every single year, and now it has so much fuel left that it's going to be able to do this for much longer than the scientists initially anticipated. These are actually known as the station keeping maneuvers, and pretty much most of the satellites and spacecraft around the planet usually have to do these once in a while. But at the same time, it has another part that was recently deployed as well, the one you see right here known as the momentum flap. And this part is basically sort of like, I guess, a sail in a sense. It's going to be pointed in such a way that the pressure from the Sun that's going to be pushing on the other parts of the telescope, and specifically on the extremely large heat shield, has to be offset somehow. And so this particular flap is used to offset a lot of this pressure and prevent the telescope from needing more fuel. And at the moment of the making of this video, it's also completed its second midterm maneuver, where it's supposed to correct any previous errors. This was also extremely efficiently done. There's only one left that's going to be putting the telescope into that halo orbit, and that's going to be done in approximately 2 weeks from now. The telescope has now officially extended some of its sunshield membranes, and the sunshield is going to be deployed in the next few days. This is probably the most nerve-wracking and also the most difficult part of this assembly, simply because here, if anything goes wrong, well, it's going to be extremely difficult to get over this. Because of the membrane's thickness, it's actually extremely thin, it's extremely easy to damage any of this. And so the actual process of assembly is going to be going on in the next few days, and hopefully everything goes well. Now, the other fact I forgot to mention in the previous video is how exactly are the scientists going to be tracking the location, the position, and a lot of other information about the telescope as it travels farther and farther away from planet Earth. Well, here there are actually 3 major stations used on planet Earth, separated by a lot of space between them. There's a station in Kenya in Malindi, there's another one right here in Australia in Canberra, and the last one is in Madrid in Spain. These 3 stations are essentially responsible for measuring the time it takes the signals to reach the spacecraft, that's to measure the distance, the Doppler shift, which measures the speed of the spacecraft, and also the actual angle between different stations in order to determine which direction the spacecraft is traveling to. And in order to avoid any potential errors or inaccuracies because of the atmospheric effects, they also then use a distant quasar to compare this to the signal from the telescope itself. And in essence, by using the data from these 3 stations, it becomes possible to know exactly where the telescope is at all times, which is also why the scientists have been able to perform such extremely accurate maneuvers so far. Oh, also, if you actually want to keep track of what's being deployed right now and how the telescope is doing, the website in the description provides you with this link, and here you can actually see what's going to be deployed next, how it's going so far, and most importantly, what each of these parts is for and what exactly they're going to be doing once the deployment is finished. And there are quite a lot of steps left here still, and some of the last ones are going to be, I guess, the most important ones. That's when the final mirror is going to be deployed as well. We also now officially have the list of all of the initial researchers and different scientists from across the planet that have already been given a go to basically be the first researchers to get some time on the telescope for various types of observations. There are a total of 286 proposals that have been accepted, and I was actually surprised to see so many Canadian universities and researchers on the list. And then I realized why this is so. Something that I completely forgot to mention in that previous video as well. This telescope is officially launched not just by NASA and ESA, it's also launched by the Canadian Space Agency. But what exactly did Canada contribute to the launch? Well, I guess, as a joke, you could say that all of the apologies for all of the delays. Sorry, eh? But in reality, Canada made 2 different instruments. The primary navigation and guidance instrument, known as FGS or Fine Guidance Sensor, and that's basically sort of like a compass, determining exactly where the telescope is pointing. But Canada also contributed one of the infrared instruments, known as NIRIS or Near Infrared Imager and Stiltless Spectrograph. And that's the instrument that's going to be looking at the universe in the near infrared, which is of course the light that we usually see from a lot of different exoplanets and also from certain types of not so distant galaxies. And 3 other instruments on the telescope are obviously provided by NASA itself. Either way though, super exciting, super interesting to see where all of this goes, and once we start getting some of the first data in I guess about a month from now, that's when we'll come back and talk about this once again. Hopefully, fingers crossed, everything goes well, and hopefully 2022 becomes the year of James Webb Telescope, the year where we actually start discovering some really incredible things using infrared light. Until then, or until future videos and discoveries, subscribe, share this with someone who loves learning about space and sciences, come back tomorrow to learn something else, and maybe support this channel on Patreon by joining the channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye. Hey yo, it's your boy Anton, introducing James Webb Telescope. Not a good new introduction.